Representing Avi today, who's unable to join us, unfortunately. We have a very interesting lineup. We have Lam Hui from Columbia, the ITC Luncheon Institute a few months ago, followed by Kishalay from MIT, Nash Sabti, and then lastly Diana Powell from the CFA. Just the normal practices, 10 minutes on the clock, and then 5 minutes of questions. And then, of course, the schedule allows no time at all for transition. And then just one extra wrinkle, I will announce this again. The fourth presentation involves embargo material. So we will be closing down the streaming system for the presentation like that. So the folks in the room have a higher level of privilege. So with that, Lam Hui from Columbia on black hole perturbations, tidal response, and
for the next few minutes, I want to tell you about work done with these collaborators on black hole perturbation theory. I only have 2 slides, so hopefully it will be brief. So in fact, I will be so brief that I won't actually explain even what this is about, except to tell you the results. So you might have heard of love number, the tidal response of an object. Black hole love numbers famously are known to be 0, which means colloquially means black holes cannot be tidally deformed, although it's slightly misleading. In any case, that well-known fact turned out recently we were able to find certain hidden symmetries, and in fact I misspelled it. You can see the Y. This is Y here. The symmetries we call ladder symmetries that actually explain this phenomenon. And without telling you exactly what love numbers are, nor what these symmetries, this is all I can tell you. You are welcome to take a look at this paper, the first one, that tell you. For those of you who love Bach, our motivation was actually this piece of music by Bach, if you recognize it. Okay, the subject that I'm going to explain a little bit more has to do with black hole ring down, right? So this is the famous event, LIGO event. You have the in spiral, and then you have the merger. And after the merger, you form a bigger black hole, generally spinning, which actually rings down like so, right? These are the ring down waveform. And to understand the ring down, the standard approach is to do the following. You take the metric and you say very close plus more perturbations, which is called H here. I'm suppressing all indices to make it simple looking. And then you take this and plug into Einstein equation and you linearize. You assume H is small. And you will get an equation that has this kind of form. It has derivatives up to second derivatives acting on H. And usually it comes with some kind of potential, which I call V. And I even sketch a potential for you. The potential actually vanishes at the horizon. It rises and then go back down. Some kind of energy barrier or potential barrier if you want. For Schwarzschild black holes, this is known as the Regge-Rieller or Serrelli equation. For Kerr, the Tarkovsky equations. Now, if you take this equation and solve it with suitable boundary conditions, and suitable means something very simple, is ingoing into the horizon and outgoing at infinity, you will find that this equation can be solved with a solution that looks like this. You do standard separation of variables, frequency omega. The angular dependence is some kind of generalized version of spherical harmonics. Think of this as spherical harmonics if you want. With number L and M, the angular momentum quantum number, and then some function of R. It turns out if you solve this boundary value problem, the frequencies actually is not arbitrary. They have discrete values, rather like the bound states of a hydrogen atom. And I give you some typical numbers here. This is using the dimensionless units, using basically setting G to 1. And you have this kind of numbers. First thing you notice is the frequency is in fact complex, so you don't just have oscillation, you have an imaginary part. The imaginary part tells you that these modes have to actually over time decay, hence the name quasi-normal modes, as you know. And there's, again, a whole spectrum of this. It's a discrete spectrum, right? So all that is very well known. And so what our investigations was motivated by the following observation by this set of authors a few years ago. They observed the following. If they analyze numerical GR simulations, they find the linear quasi-normal spectrum fit the ring down fairly well, even at the time of merger. So the standard law, at least before this paper, was, well, you should wait until the perturbations kind of die down so that perturbation theory is acceptable. And then you can use linear perturbation theory to describe what's going on. But this paper actually show, by analyzing numerical GR simulations fully nonlinear, that the linear quasi-normal spectrum actually fit the data fairly well, even at the time of merger, where the perturbations are supposedly large. So that motivates our kind of two separate projects. The first project is to ask, okay, well, let's investigate the nonlinearity, and the kind of obvious thing to do is to go to second order. So instead of linearizing Einstein's equation, you keep the second order terms. And schematically, it will look something like this now. On the left-hand side, you have the same Tarkovsky equation, basically. But on the right-hand side, you have some kind of source now, which goes like the metric perturbation square. So you have this kind of form. And if you imagine taking this H and break it into first and second order, it's very easy to see. Then the second order contribution from H now has a source from first order square. And it's not hard to see. Then you should expect quadratic quasi-normal modes. Let me give you an example. If 2, 2, 0, this 2 and 2 stand for L and M, 0 stands for the fundamental mode. This is actually the primary ring down mode for a lot of systems. If you take two of them and combine them, you will get a new frequency. That is basically what this equation would predict. If you put in two linear quasi-normal on the right-hand side, you would generate a mode with this kind of frequency. Just add the two frequencies together. It's kind of an obvious thing to observe and actually check. And we were able to actually confirm that analyzing black hole merger simulations, numerical GR simulations, indeed, we were able to find the existence of these quadratic quasi-normal modes. So that's number one. And we have a number of checks that convince ourselves that this is actually real. The second point I want to make is the following is a separate project with Macarena Lagos. We analyzed the space-time structure of the Green's function. This is the Green's function that determined both the second order quasi-normal modes and also actually the generation even of the linear modes. And it suggests, that exercise suggests, in fact, these quasi-normal modes, both linear and high order, they are not actually quite generated at the horizon. They are generated at the peak of that potential, basically this potential, which is more around 3 GM rather than 2 GM. And so maybe the fact that perturbation theory works so well, even at the merger time, tells you even though the perturbations are expected to be large, very close to the horizon, maybe they are not that large, actually around the peak of the potential. Maybe that's what's going on. A lot of work remains to be done on that. And lastly, let me just close with why is this interesting? If we can detect high order modes, including quadratic ones, in data, which we believe will happen in the future, obviously you will improve measurements of the black hole mass and spin of the final black hole. And you also offer sharper tests of general relativity, right? Because this structure, the precise structure and coefficients is really predicted by Einstein's equations. And so checking basically these higher order modes is basically a check of the nonlinear structure of the perturbations around a curved black hole. So it offers kind of more avenue for tests of general relativity. I'll end here. Thank you.
So Lam, you may have said this, but in your expansion on the top left, the
Yeah.
error plus h.
Yes.
You have to assume then some rotation parameter for t curve?
Yes,
Where
absolutely.
does that come from?
Absolutely. So this curved black hole has a rotation, so that has to be put in. And so you have to know basically what is the final spin of the eventual black hole. So you expand around that eventual black hole.
So where does that knowledge come from?
That knowledge comes from basically measurements. So you can either try to predict it from numerical GR simulation, knowing whether basically the progenitors, what kind of progenitors, you have the mass ratio, for example, and their spin. You can try to predict it, or you actually have to measure it with a realistic system. You have to measure it, and in fact, the way you measure it is by actually checking out these frequencies. I should have said, here I assume the spin of the black hole is 1/2 of maximum. If you change the spin, these frequencies are going to shift. And so you can try to fit for the spin using precisely these quasi number modes.
Okay, thank you. Are there any other questions? Cool, thank you very much.
Okay, perfect. Okay, so we're going to switch gears from black holes to things that are much less massive, which are low mass stars and exoplanets. So to be honest, I'm a bit uncomfortable with this because I never thought I'd be giving a talk on exoplanets because I'm a kind of an astronomer. Usually the things I think about are things that are erupting or exploding in some form or the other. The ones that sort of use infrared surveys to find transient. The story for this source, actually, it's interesting to actually look at the history of what these nova eruptions, how we know about these nova eruptions. So start with this figure. So if you go back and ask which is the first historical record of a nova in Western history, it turns out it's this particular source over here. It's this red circle that was pointed out by Hevelius in the 17th century. And for a long time, this was considered to be the first example of a nova in the Milky Way that's recorded in Western history. It is a white dwarf with a low mass companion that's undergoing some type of thermonuclear eruption. So it's natural to ask, what does the nova look like today, 4 centuries after the eruption? And when you do that, it turns out that it looks something like this. So in the right, you see this beautiful multi-wavelength image. In blue is the optical emission lines, which has this interesting geometry. There's a dust enshrouded remnant in the center. And in these bipolar outflows, you see molecules. These are CO molecules that are shining. And obviously, this is a very interesting geometry, except it turns out that when you ask what do other novae that we've confirmed subsequently look like, they actually don't look anything like this. Or the other way of saying this is that the first claimed record of a nova actually looks very different from anything we see from white dwarf novae. So what that immediately makes you suspicious, maybe this is actually something else, not quite a white dwarf nova like we think of. Turns out that when you do the investigation, what this source looks like is actually a different class of objects that also look a lot like novae, which are the so-called red novae, and which we now identify with these phenomena that come from stellar mergers. So why are these called red novae? So here is an actual time-lapse image from Hubble showing the eruption of the star called V838 Mon. The expansion that you see over there is actually just a dust echo from the eruption that is illuminating this dust cloud. And as you see, with time, this transient becomes extremely red. So by the time, in a few months after the eruption, what you see is that it becomes a purely infrared dominated transient, and you see that in the spectral evolution as well. So it goes from looking like an F-type star around the peak of eruption to something like an M-type star. It's a very cold star. And that's completely different from what we see in any other type of nova eruption, for sure. Novae show lots of beautiful emission lines. So to summarize, they show these, they start off as these relatively hot transients. They become redder with time. They have these cold photospheres that start looking like M stars in a few months. And they keep shining in the infrared for years and decades afterwards because of all the dust that's formed in this cold photosphere. So it turns out that because we now have these amazing time domain surveys that are surveying the sky, you can actually find them quite easily, especially even in other galaxies. So what I did here was show you a phase space of the luminosity on the y-axis, peak luminosity as a function of the duration of the outburst for all of the events that we've known in the past. The most luminous events that you see on the top that reach 10 to the 42 ergs per second, these are the luminous red novae that we can find in other galaxies. And the lower luminosity ones are naturally ones we can find only in our own galaxy. And it turns out that you can explain the properties of these light curves with hydrogen recombination, very similar to what we see in type 2 supernovae. And if you assume that, you can actually lay down contours of ejecta mass on this, which is to say that how much outflowing material would you need to explain the duration of the light curve and the energetics of the light curve. And you can read off right from this plot that the faintest events that we've known of go from anywhere about a fraction of a solar mass of ejection to something like tens of solar masses of mass being ejected from the most massive binaries that would exist in the universe. So the way I approached this was that I wanted to find more of these, and let's see. Okay, and what I was looking for are things in the galactic plane for the low luminosity objects that would be ejecting very small amounts of ejecta, and those would be naturally less luminous. So that's where the story of this event begins. There's this rather inconspicuous star, I would say, that exists in the galactic plane. This is an image that was taken with UCURT 12 years ago. There's this reddish source at the center, which you would otherwise not quite pay attention to. But it turns out that in 2020, this star did something remarkable, which is that the Zwicky Transient Facility Time Domain Survey actually spotted the star to brighten by about a factor of almost a few hundred in flux. This is the light curve, flux as a function of time. It underwent this outburst that reached about 17th magnitude in the optical bands. And you would otherwise not quite pay too much attention to an outburst like this. There are always things erupting in the galactic plane. But I was interested in this object for other reasons. And what I did was, even after the optical outburst faded away, I went back and took a near-infrared image of the field. And it turns out that even after the optical transient had sort of disappeared, there was this huge near-infrared source that was still lying around. So I was like, hey, why is it still shining in the infrared? So you do some more investigation. It turns out that the WISE satellite was observing the same part of the sky. It also has this huge mid-infrared counterpart that is still lasting even today. Like WISE is still seeing the infrared emission even though the optical transient is gone for more than a year. So fortunately, because I was interested in this object, I took a spectrum of this with, this is an optical spectrum of the source. I thought it would turn out to be a nova. It's definitely not a nova. The spectrum actually looks more like an M star, if you will. It only has these cold molecular absorption features. You would otherwise classify it as an M4 type star. And it actually looks strikingly similar to what we see in previous examples of this so-called class of red novae, which are stellar mergers that turn into these very cold M-type stars in a few months. And the similarities are also similar when you sort of just try to see how the luminosity and the temperature of the source evolved. On the left, you see in black, I'm showing the luminosity evolution. It reaches a peak luminosity of about 10 to the 35 ergs per second, and then it fades away after showing this plateau. Similarly, you see temperatures that are of the order of hydrogen recombination temperature. So all of it sort of ticks all the boxes that we need. It has a characteristic redward evolution of the spectrum. It becomes infrared dominated in a few months. It has this cold photosphere, and it becomes dust enshrouded, as we see from the WISE data. So okay, so like you take a step back, like okay, there's one more stellar merger, that makes it the 6th one in the galaxy. So what? Except until you start comparing it with the other objects that we know of, which is if I come back to this plot and you ask where does this guy live in this family, and it's about a factor of 1,000 fainter than anything we've seen before. So you ask why is it a factor of 1,000 fainter? And if you just read off that plot, you would see that the amount of ejecta that we're dealing with here is of the order of a Jupiter mass or less. So you have a stellar merger that instead of ejecting a few solar masses of ejecta, actually ejected a Jupiter mass of ejecta. And so we went back and started looking at the progenitor. So this is a Gemini AO image, which allowed us to see what the progenitor actually looks like. And if I won't get time to look into this, but essentially if you just look at the progenitor and take your best dust models, it turns out that the progenitor actually looks pretty much like a sun-like star. So it intersects the position of the progenitor on the color magnitude diagram actually intersects pretty well with a 1 solar mass star that's barely starting to evolve off the main sequence. And and this is all based on very faint progenitor photometry. So take this with 1 Jupiter mass of salt, because it is a tricky measurement to do. And if you try to put all of this together, say why does this particular stellar merger event look 1,000 times fainter than anything we've seen before, then the energetics work out to a situation where you have a companion that was so less massive, so on the order of a Jupiter mass, that the amount of energy available was enough only to eject a Jupiter mass of ejecta. So Morgan here, that's when Morgan and I started talking, and then you see if you do all of the take the pre-outburst data on this source and see the amount of gas that was ejected by the system prior to the outburst, it all is consistent with a mass ratio of the order of a few hundreds. So you have a sun-like star with a companion that's of the order of a Jupiter mass that's producing this outburst that looks like a red nova but 1,000 times fainter. So we were very excited about this, and we actually got a JWST observation of this as well as part of a GTO program. This is a JWST image of the field. This is the transient that's still detected. So I think we've gone off to a good start. We have the correct target in the slit. For the observers in the room, you would realize how hard this is in the galactic plane field, and the SNR is better than expected. And I just came to know that this might have been the first TOO on JWST, so we were so excited about this that I made this t-shirt. So if you're excited about this event, we will give you a free t-shirt as well. Okay, so here are my concluding thoughts. So this event represents stellar merger phenomena, except in the energy regime that we've never seen before. And it really is a type of phenomena that we would see only in the galaxy, coming from planets being engulfed. And we haven't had completely explored it yet, but I know Morgan is working on this. But the response of the stars to this planetary engulfment is rather curious, and we are expecting to find more of these in the coming years, combining optical and infrared surveys. So I'll end over there. Thank you.
So your notion of this planetary engulfment, is it a gentle settling or is it a crashing in head-on?
Oh, I think it's a gentle settling. At least that's what I mean. Morgan is probably better equipped to answer this, but what you're seeing is you have a star that's starting to evolve off the main sequence, and it's running into the planet as that happens. And that's my nominal notion, but I don't think we have enough data to rule out the other situation, which is maybe it's being scattered by another planet into the star. I don't think that there's data to really distinguish the two, but I think the natural way to think of it is that you would have a star evolving on the main sequence, and the planet is slowly sort of coming, being engulfed by the star, and at some point it's merging with the core of the star, and all of this energy is being dumped into the envelope of the star.
I have a question about the spectra that you showed me.
Yeah.
Like the first third of the talk.
Yes.
So, first of all, the features look pretty weak to me, and it looks like something like a luminosity M star,
right,
rather than high-redshift. And then the related question, you see in the other three spectra you plotted, there's calcium triplets.
Right.
And there's no calcium triplet in your source. So
right.
Any idea why this might happen?
Yes, so I think one of the things is that if you look at the phase at which these spectra were acquired, all of the other sources were observed maybe a month or two after peak, but because this one was a low luminosity one that didn't quite catch our attention, the spectrum is at a very different phase. And from my understanding, if you look at other objects at similar phases, there is quite a bit of variation, especially in the calcium triplet line as a function of time, because you're really looking at this very complicated photosphere that's evolving with time. And I agree, the features are again weaker, but what the weaker features really tell you is that it's a hotter photosphere, because you would, as the star gets cooler, the molecular features become stronger. So, and this is something we talk about a lot in the paper, which is that because you have a much gentler disturbance to the star sort of doesn't quite cool as much as you would like in the other events, which have much more violent disturbances to the star itself.
Can you rule out an alternate mechanism for this? Namely, if you took our solar system as an example, and you rheostated up the luminosity of the sun, let's say by a factor of 1,000, you would get the mass sublimation of ice from trillions of Kuiper belt objects, and that would carry with it a lot of dust in that rapid sublimation.
Right.
Is that consistent with this or inconsistent with what you're observing?
Right, I'm just wondering what causes the sun to suddenly brighten by a factor of
Well,
1,000?
I mean, if you take an AGB star, for
Right,
example.
yes.
So it's evolving off the main sequence,
Yes.
as you indicate here.
Yes, yes.
The luminosity of an AGB star can increase as much as 10,000, which may be more than in this case.
Right.
And it's fairly straightforward to show that that luminosity increase would dramatically affect the Kuiper belt objects, which we think carry a lot of ice.
I think the other issue is the time scale. This is brightening by a factor of 1,000 in 2 weeks.
Well,
That would not be possible in the case of stellar evolution, I would guess.
well, yeah, I'm just asking whether the
Yes.
infrared proton,
Yeah.
could be consistent with the dust that is ejected along with this rapidly
Right.
sublimating water ice.
Yes, I think the infrared properties could be explained in several ways, and that's sort of one of the limitations in finding more of these events, because there are many things that change on slow infrared timescales, but seeing something suddenly brighten in the optical and over timescales of weeks is really, I think, something that we are looking for as we try to find more of these events, which is that I think several stars could do the kinds of it would be harder to sort of put that together with a week or two by so much. But in the infrared properties you could probably explain, yes.
Take one more quick question.
Could you go to the plot where you have like all of the events, including the
Yes, sure. Yes.
connection?
Yes.
So like, what is? I mean, it looks like the V433-2 SGR is also pretty low mass. Like
Right.
what is it? Like 1 to 10 Jupiter mass, like a few
Yes.
Jupiter
Yes,
masses.
yes.
What do you think
Yes.
that is?
Yeah, so that one is an event that was, I guess, recognized in hindsight, and the data for that event is a bit sketchy because it was really identified in the 90s. So I think the peak luminosity in that case can be very easily underestimated because we didn't quite see the peak of the eruption, and maybe a few months later someone said, hey, there's a star that is brighter there. That was not quite the case before. So I think you have to take, I guess we have to take that with again a Jupiter mass of salt, because I don't think there's great data over there. But yes, I think all of these, especially both the V4332 SGR and V1309 SCO. V1309 SCO is, we know, is a 1 solar mass star with a 0.1 solar mass star, and so I think that's in that similar regime. That would be my guess, which is sort of a mass ratio 10-ish binary.
I think we need to move on.
Yeah.
Thank our speaker again. Here from Nash Sabti from Johns Hopkins University. The GALLUMI ecosystem, a simplified framework for cosmology with high-redshift galaxies.
Does anyone know who they are? Saba, yeah. I'm not entirely sure why. There we go. Right. Well, it's a pleasure to be here. My name is Nash Sabti, and I will briefly tell you a bit about ongoing work that I'm involved in, where the main idea is to build a unified framework to learn about cosmology with high-redshift galaxy probes. So let me start off with the big picture. This plot here shows the scales that we can probe as a function of redshift. And the right axis shows, roughly speaking, the corresponding halo mass at redshift 0. Now, most of our current understanding of the properties of our universe It's really either based on observations of the cosmic microwave background at a ratio around 1,000, and on a number of local universe probes that range from Milky Way satellite observations to reclancing surveys, galaxy surveys, and so on. The area that's enclosed by the black line shows when nonlinear corrections become very relevant, and this could make some of the analyses of these probes much more complicated. But nevertheless, these data sets already show us a rich evolution of cosmic structures. Started off as tiny matter fluctuations at the time CMB decoupling, that then hardly grew to become the observed large-scale structure today. They have established what we now know as the standard model of cosmology that tells us, for example, that there is dark matter in the universe, and that this dark matter is, roughly speaking, cold and collisionless at supergalactic scales. But there still remains a large number of questions unanswered, which is especially the case within the context of the dark matter. And I'll be focusing on the dark matter a lot here. And so this naturally means that we need to come up with new or better ways to search for the possible properties of the dark matter. And of course, there are many different ways in which this can be done. For example, we could try access smaller scales that are currently being probed, where the dark matter microphysics may have left a relevant trace. Or adjacent to this, we could go to higher and higher redshifts, where the modeling becomes a little bit less complicated, where structural formation is still in the nonlinear regime, but not in the deep, deep nonlinear regime. That is, where besides central galaxies, we don't really have to worry about satellite galaxies, where the astrophysics is still super duper complicated, but it is not necessarily overwhelming our ability to say anything about cosmology. And it is in this regard where high-redshift galaxy probes could provide us with a helping hand. And that's simply because the first few generations of galaxies that populate our universe during the eras of cosmic dawn and ionization, they reside in dark matter halos that were much less massive than their counterparts today. Now, from an observational point of view, the next 10 years promise to be a very exciting years. So we, of course, have the Hubble Space Telescope that's been around for a while. JWST is up and running and is building upon the legacy of the Hubble. We have the Roman Space Telescope that's launching in a few years. And all these space telescopes are able to directly image galaxies at very high redshifts. On the ground, we have experiments such as Hera that is aiming to measure the 21 centimeter power spectrum during the cosmic dawn era. We have telescopes such as Subaru that have already provided us with measurements of the correlation function of high redshift galaxies. And we have observatories such as COMAP that aim to use line intensity mapping techniques to probe the era of cosmic ionization and beyond. And it's really the combination of data sets generated by these telescopes that has the potential to significantly improve our understanding of the high redshift universe. Now, at this point, let us take a step back and let's ask ourselves, what can we actually learn with the data that we currently have? Now, with current data, I of course mean data by the Hubble Space Telescope. The Hubble has been observing galaxies at high redshifts for decades now. We have beautiful images like this one here, which is an example from the Hubble Ultra Deep Field Survey. Now, such an image provides us the abundance of galaxies as a function of their luminosity or magnitude, which is what we call the luminosity function. And so a question we can ask here is, what can this luminosity function of galaxies tell us about cosmology? For example, about the clustering of matter. And to answer this question, we need to understand how the luminosity function is constructed. So I use the symbol phi for the luminosity function, just a number density per unit magnitude. And in general, it can be separated into two components. The first one is the halo mass function, which is mainly affected by cosmology. And the second one is the relation between halo mass and the magnitude of galaxies residing inside those halos. It's also called halo-galaxy connection, and it's driven by astrophysical processes. Now, from the cosmology side, we have relatively good control over uncertainties. That's because the physics of our dark matter halos collapse and form is reasonably well established, especially given the guidance we have from simulations. Okay? Now, one of the main challenges here is that some of the cosmological effects that we are interested in could be mimicked by astrophysical effects, such as feedback processes. So ideally, we would like to separate these two contributions as much as possible. But this then also means that we need to come up with a way to relate halo masses to the magnitudes of their residing galaxies. Long story short, things are very uncertain when it comes to the halo-galaxy connection. One of our current best guesses is that we think that it might involve some kind of a double power law function. And the reason why is that when we plot the ratio of stellar mass divided by halo mass as a function of halo mass, we find that this ratio exhibits a peak somewhere around 10 to the 12 solar masses, somewhere around the mass of our own Milky Way halo. Then the idea is that for lower and larger halo masses, star formation proceeds less efficiently due to a number of baryonic feedback processes, as mentioned at the top there. And the double power law function is just the simplest function you can think of that can capture this trend. So with this assumption, we can compute the Galactic connection term in blue and obtain the dependence of the luminosity function on the 3 parameters in our model. The first 3 panels show the impact of the cosmological parameters, sigma 8, which is the matter clustering amplitude, omega m, the matter density parameter, and ns, which is the spectral tilt of the fundamental power spectrum. The next 4 panels show the impact of the astrophysical parameters. This is a busy plot. I won't go into the details. I just want to highlight the degeneracies that exist between cosmological and astrophysical parameters. So for example, if we plot the red curves on top of the blue curves, we find that at the level of the luminosity function, an increase in sigma 8, so an increase of the matter clustering amplitude, could be mimicked by making galaxies brighter, so by increasing epsilon star. And so when it comes to cosmological parameter inference, it is very important that we marginalize overall astrophysical parameters. And we do that in GALLUMI. And in its first iteration, GALLUMI is built as a galaxy luminosity function pipeline in the form of a likelihood code that is implemented in the MCMC sampler MontePython. And the reason why we chose MontePython is because in this way it can be readily used with other data sets. Think of Planck CMB data, Pantheon GA supernovae data, and so on. The current version contains different models for the Galactic connection, different Halo mass functions, different dust calibrations, and really allows the user to check how different assumptions impact the results. And so recently we applied GALLUMI to learn something about the clustering of matter. So this plot here shows the linear matter power spectrum as a function of wave number. The dots with error bars, they are data points from a number of different probes, as mentioned there. And the black line is some best fit curve for a cold dark matter cosmology. Now, going back what I mentioned earlier, we are very interested in the small scale behavior of the dark matter. And so we used GALLUMI together with latest data from the Hubble Space Telescope. We ran a firm CMC analysis. And we found that we can obtain these 2 new measurements of the matter power spectrum. And you see that with current luminosity function data of galaxies, we are able to reach scales of about 10 inverse megaparsecs with an error of about 30 to 40%. So going back to the summary plot I showed earlier, it means that we are now able to probe combinations of scales and redshifts that were previously unexplored. But we can take this idea even further. And when I say further, I really mean 2 things. 1, we want our results to be stronger. But 2, at the same time, we want them also to be more robust. And so this really translates into having a better handle on the Galactic connection. And the way we aim to do that is by considering different probes that all depend on the same Galactic connection in one way or another. So we've already dealt with the luminosity function. Next up is the clustering of galaxies at high redshifts, the 21 centimeter signal and line intensity mapping. Then the idea is to combine these probes together, okay? So that not only will we have a better handle on the Galactic connection, but also a better handle on cosmology. And all of this will be done within the GALLUMI framework. So the modeling, the combination of data sets, parameter inference, and the extraction of cosmology and fundamental physics. So all this is still work in progress, and if any one of you happens to be interested in this, I'll be very happy to chat. Yeah, that will do it from my side. Thank you.
So I have what's probably a naive question. You drew attention to the transition from linear to nonlinear in particular. Is that because that's where you're most sensitive now, or is that because you think that's where the physics is going to be most?
Which linear to nonlinear connection do you mean?
If you could go back a slide or 2. Yeah, there.
Uh-huh.
You got that black curve shooting here.
So I would say that area enclosed by the black line is just where the data analysis becomes, well, the analysis of data, it's there, but it's just the interpretation in terms of how can we learn about cosmology in that region of parameter space. It becomes very, very complicated. And I think my understanding is that in some cases people really just throw out data. They don't consider data in that regime there. Yeah.
Oh, go ahead.
So how do you account for scatter in the luminosities?
Yeah. So let me see if I can slide about this. Oh, well, I guess. So this shows like our models for the halo-galaxy connection. So what we do is that so for our model, it's not applicable to the level of individual halos and galaxies, right? Because the model doesn't depend on the unique formation history of different dark matter halos. It only depends on the halo mass. So whatever magnitude we derive from galaxies only depends on the halo mass and some astrophysical parameters, right? So what we do is that we treat this magnitude as an average magnitude, and then we assume a certain distribution of magnitudes of galaxies like dark matter halos with this average, and so with sigma and UV that we marginalize over in the analysis.
Thank you very much.